Hi everyone and welcome back to our YouTube channel. In this lecture, I show you another example where we will compute the determinant of the given matrix using Laplace or cofactor expansion method. And here's the matrix given to us in the beginning. Let A be this matrix here. So we are given a 5 by 5 matrix in this time. Okay. In this case, now we have 5 rows and 5 columns. And what we are required is to find or to compute the determinant using the cofactor expansion method. Okay, then what's the first step? So, in other words, how should we start? Okay, we need to select one of the rows or one of the columns to expand the determinant. Okay, and what is our criterion to choose this row or column? Okay, as you remember, the more zeros means the easier computation. So I examine through the rows as well as through the columns to see in which row or column I have many more zeros than the others. And if you notice, let's use another color here. So if you look at the third row here that I just surrounded for you in red color, you see we have 4 zeros here, right? So we have 4 zeros and only one non-zero element. And that means it would be more convenient for us to start with the third row. So in other words, we will expand our determinant along the third row. And what is the formula again? Okay, now we're computing the determinant of the matrix A by using Laplace expansion method. And here's the formula. As we all remember, since we have 5 columns and I selected the third row, so we have 5 columns, then that means column number is going to change. We start from g is equal to 1, which represents the column number, up to 5, right? So, and then we have, since I choose the third row, this first index would be 3, and this is j, 3j, because the index for the summation is j, which is the column number, right? This stands for the column number. And what we have here, we have the cofactor, right? So we have also cofactors. And if we expand this summation, what we have is, okay, for g is equal to 1, we have A31, C31, and again here Aij values are the components in the original matrix, and in our case in the matrix A, and Cij values are the cofactors. So we need to find the summation of these multiplications. And since I choose the third row, then I do this process using the third row. Okay, and A32 times C32 and A33 times cofactor 33 plus A34 times C34, and at last we have A35 times C35. Okay, now here's the good news. Even though we have 5 terms in this summation, you see we have 5 components in this summation. Well, the good news is, if you notice that all the entries in this row besides the first one are equal to 0. So I just pointed out here. So this value is equal to 0, this value is equal to 0, and this value is again equal to 0, and this one is also equal to 0. So that means we don't need to compute the cofactors or the values for the cofactors where we multiply by 0, right? So this is equal to 0, this term is 0, this term is 0, this term is 0, and this term is 0, because no, regardless of what the value of cofactor, multiplying it by 0 will give us a 0. So we don't need to find the cofactors, and this makes our computation pretty much easier, right? So you see we have a very easy computation here. What should we do? Okay, the only thing we need to do is just compute the very first term in this summation. So A31 is equal to what? It's equal to 3, right? And what is the value of the cofactor that corresponds to this entry of the matrix? Well, the 3 one, right? So how would we find that? Minus 1 to the power of I plus j, and here I is equal to 3 and j is equal to 1, so we have 4 for the power of minus 1, and this value is equal to 1, right? Because even powers of minus 1 is equal to plus 1, and odd powers of minus 1 is equal to minus 1, so we have plus 1 here, so that doesn't change the sign. And we also need a determinant, right? So if you remember, we have the minor here, so we need to find M31, which is actually the minor, right? So we need the M31 component here, so which is a determinant that we find by deleting the third row and first column. So getting back to our matrix, so if you notice, we need to delete the first column and the third row, and then write all the remaining elements, and then find the determinant of the new matrix. Okay, so this is the way we find the minor, right? So we are looking for the minor that lies at the intersection of the third row and the first column. So how can we find that? So we just delete the third row since I is equal to 3, and we delete the first column since j is equal to 1, and then just put all the remaining values in the determinant form, and we have a now 4×4 determinant. All right, so first of all, let's erase this because it may exceed this. Okay, so let's write what is left behind. So we have in the first row, what is left? 1, minus 1, minus 1, and 2. And in the second row, what is left? So without changing the order or elements, I just put the elements as they are. I don't play around them. So I just put them as they are: 1, 0, 1, and 2. And I pass to the fourth row, and I have minus 1, 0, 0, and 1. And in the last row, what is left there? So we have 1, 0, 1, and 2. Alright, now this is our new matrix. In other words, this is our new determinant. And in other words, since we are given a 5×5 matrix, then when I apply Laplace method, then now in the second step I have a matrix of size 4×4, and in the next step I will reduce it to 3×3, and in the following step I will reduce it to 2×2, and this step keeps going on until I reach to some kind of base case when our base case is a 2 by 2 case, right? We know how to find or compute the determinant of a 2 by 2 matrix. It is very easy. So if I come to that point, then I am done. And I put the values back in the place and then return the value. Okay? Return the total value after, of course, multiplying what is required. Okay, let's continue. Now I have a 4 by 4 matrix, right? And actually I need to compute this determinant. This is the new determinant, right? So use another color. Okay, now let's use a black. So this is our new matrix. Then what should I do? Okay, let's continue. We have 3 times plus 1 here, so let's put 3 outside the parentheses and let's make use of a parenthesis to avoid confusion because we continue to the computation process. Okay, now which row or column should I choose to expand? In other words, to compute this determinant, this new determinant, which row or column should I continue with? Okay, and our strategy again is the same. I look at the rows and columns and I prefer the one which has more zeros than the others. And if you notice, if you take a closer look at all the rows and columns, you see that here in the second column I have 3 zeros and only one non-zero element, so which is very convenient for us to choose. So if you choose the second column, then we only need to make one multiplication, right? So let's do that. Suppose I choose the second column and now I expand my determinant with respect to that column. So here's the new formula. And if you notice again, the only non-zero element is -1. So this is actually the only value that I need to compute. I don't need to compute these values, these zero values, because 0 times cofactor is again a 0. So I don't need to compute the zeros. That's why I choose the second column, right? Otherwise, I can choose any row or any column that I want, because that wouldn't change the value of determinant at all. That just makes our computation or computational process easier. That's the way actually why I choose it. Okay. Now, the only non-zero element is, well, with respect to this new matrix, it is the 1, 2 component of the 4 by 4 matrix, right? So what I have is -1, okay, times -1 to the power of I plus j, and in this case, since this is the component 1, 2, we have I is equal to 1 and j is equal to 2, right? Because this element is actually at the intersection of the first row and the second column, and times the minor. So how can I find the minor again? This time I delete the first row and I delete the second column, right? Because -1 is placed at the intersection of the first row and the second column. So I delete the first row and second column and then put the remaining values in the newly obtained determinant. So now we will have a 3 by 3 determinant. Okay, so we continue to reduce the size of the matrix. We had a 5 by 5 matrix in the beginning, and in the second step we had 4 by 4, and now we will have actually 3 by 3. Okay, things started to be easier. All right, let's write the remaining elements. So we have 1, 1, 2, -1, 0, 1, and 1, 1, and 2. All right. Am I done with my computation process? No, not yet, because this time now I have a, as you see, I have a 3 by 3 matrix who is determinant I need to compute, right? But this time I have a much smaller size. So I had 5 by 5, but this time now I decreased it to 3 by 3. So only one more step would be enough for me. And again, I need to choose a row or a column and then continue to our computation. And don't forget to put the values here. This is -1. And this is also -1, right? Because -1 to the power of 3. 3 is an odd number. So this is equal to -1. And -1 times -1 is +1. Times 3 is 3 again, right? So no change on the sign. We're lucky. So just put it in its place. And use the parentheses again to avoid confusion. Okay, now in the new one, again, I use cofactor expansion method once more again. And which row or column should I choose? Well, it's better always to choose the one which has more zeros, and there's only one zero, so I can choose either the second row or the second column, doesn't matter actually. So suppose I choose the second column, right? Second row. Suppose I choose the second row. Okay, now again apply our Laplace expansion method once more again. So what do I have now? If you notice, now if I take the first element, we have -1 at that position, right? This is component 2, 1, -1 times, don't forget -1 to the power of I plus j, because that comes from the definition of minor. So this time 1 plus 2 again, and times the minor. And what is the minor here? So this time we have a 2 by 2 matrix or determinant, right? So if let's use again a different color. So if I delete the first column and second row, and then what is left behind? So we have 1, 2, and we have 1, 2 again, right? It's interesting. So that makes things even easier if you notice one thing here. Okay, let's continue, and then we'll come to that pointer later in a short time. So plus, okay, now look at the second value. So this is 0, so I don't need to write it at all, right? Because 0 times cofactor again is 0. So let's proceed to the last one, which is 1. And this is the actually component 1, 3, right? Because this is, so sorry, 2, 3. And well, right, so 2 plus 1, it's the same. And now this is 2, 3. So this element, which is 1, lies at the intersection of the second row and third column. So we have 1 times the value is 1, so we have -1 to the power of 2 plus 3, 2 plus 3, and times the minor. And what is the minor here? So this time, okay, this time I need to delete the third column and second row, right? So third column and second row. So what is left behind? So what is left behind is 1, 1 and 1, 1. All right, now let's look at the situation. So what's the determinant of this 2 by 2 matrices? It is easy. So how do we find? We produce this formula by using the definition of the determinant, right? Using permutations and their signs, and this is actually equal to 2 times 1 minus 1 times 2, and it's equal to 0. So the good news is, since it is 0, right? This determinant is equal to 0. Then 0 times something else, again a 0. So this term is exactly equal to 0. And how about the other one? And again, if you notice that this determinant is also equal to 0, right? This is 1 times 1 minus 1 times 1. So 1 minus 1 is equal to 0. And this determinant is equal to 0. And 0 times something else, again equal to 0. So this term is also 0. So 0 plus 0, 0. And what is the result? 3 times 0 is equal to 0. And that's the end of our journey. Alright. Now we found the determinant. So we obtained the value of the determinant, which is equal to 0 for this given matrix A. And we computed our determinant this time using Laplace or cofactor expansion method. And how would we do that? Well, our strategy works well when we start with the row or column which has actually more zeros compared to other rows or columns, and we keep going on the same manner, and we expand our row or column to compute the determinant. And actually what does it mean is, what it means is, in the beginning we had a 5 by 5 matrix, and then in the second step we have a 4 by 4, and then applying this technique will yield a smaller size of matrix each time we continue, right? And we continue to this process until we reach to the 2 by 2 case. And since it is very easy to compute the determinant of a matrix of size 2 by 2, then we put the values there and then find our result. Alright guys, that's it for this lecture. And in the next lecture I will show you a very important rule that's called Cramer's rule to find the solution set of a given system of linear equations. And Cramer's rule only makes use of determinants, and in the next lecture you will see how we will do, or how we will use Cramer's method to find the solution to a given system of linear equations. And until then, have fun and see you in the next lecture, guys.